Captain Chaudhari. I'll be speaking about a few other projections. They are very interesting, and it is particularly important to know about these projections. We have been seeing these projections, but we never realize that the projections are of different types. So let us look at some of these projections. They are interesting that way. So the first one in this category is Clark's minimum error perspective projection. Now what happens is, the projection is azimuthal. For example, we are trying to project on the plane. Now the thing is, it looks like a mnemonic or a stereographic projection with a difference that instead of the projection point, the source of light being at the center or at a point diametrically opposite, is 1.36 times radius to 1.7 times the radius from the tangent point. And what happens is, the projection point is chosen in such a way that the area of interest is projected with maximum accuracy. Okay, now let's talk about Lambert's polar zenithal equal area projection. Now what is the specialty of this projection? Let us say here's a globe, and let us say here's the tangent point. Let us select on this particular meridian, okay, the various points up to 4. Say these points are A, B, C, D, E, and so on. Now, what is the actual distance from the tangent point to these points in space? Not along the meridian, not along the surface of the earth, but in space. So this way we can project the entire globe except the point which is diametrically opposite. So let us project the entire globe and see in this projection how it looks. We can project the entire globe except the diametrically opposite point. So suppose you are looking at the globe from front of, say, Middle East or something like that. You will find the entire globe like America, North America, and then South America, and then there's this Africa and Asia, Russia, China, and Australia coming like this, and so on. So in this projection, what you are seeing is not 50% of the globe, you are seeing the entire globe. Suppose the tangent point is this, so whatever is three-dimensional distance in space, not the great circle distance, not the distance along the surface of the earth, the actual through and through distance to a point is represented. So in a way we have converted three-dimensional globe into two-dimensional disk. So that is Lambert's equal area zenithal projection. Next is Gaul's stereographic cylindrical projection. Now this is partly cylindrical, partly stereographic projection. The idea is you try to resolve the problems of normal Mercator projection where the polar regions are not projectable. In this projection we can actually project the entire globe, we can look at the entire globe. The name of projection, the Gaul's stereographic cylindrical projection, actually has the property of cylindrical as well as stereographic projection. What happens is, if you imagine the globe, once again made up of transparent material with, let us see where we'll put the point source of light. The cylinder is not circumscribing the sphere, but in the latitude 45 degrees north and 45 degrees south, the cylinder is cutting the globe. So basically, here's the cylinder, right? The common points on the cylinder and the globe, or the points of intersection, are the parallels of 45 degrees north and south. Now imagine these 2 points are diametrically opposite. On the equator, you have the point source of light here. Now what will happen is, the light is switched on and everything which is there on the globe gets projected on the inner concave of the cylinder, which means that if you have parallels of latitude like this, the point of projection of this point will be found by drawing a line from here to this point. Then the point of projection of this point will be found by drawing a line this way over here, and this particular parallel of latitude over here, this particular point on the parallel of latitude would be projected like this. So if you look at the projected points, you will find that as you go away from the equator, the distance between the parallels of latitude is gradually increasing, and actually the pole also can be projected. In fact, this entire line over here and this entire line over here represents the pole. So pole is represented by a straight lines parallel to the equator. Now in this projection, the meridians will be more or less equidistant parallel lines, north-south running parallel lines, whereas parallels of latitude are east-west running increasing distance parallel lines. If you talk about distortion, shape, orthomorphic nature, etc., everything is compromised, but the advantage compared to the Mercator projection is the polar regions are also represented. You can actually represent the entire globe in this. So the beauty of this projection is you have chosen a point outside the cylinder. You are able to actually project and view the entire globe on the inner concave of the cylinder. Appearance would be something like this: increasing distance of parallels of latitude as you go towards the pole, and the pole is represented by the straight line. Next is Bohn's modified conical projection. Now suppose this is a central meridian. Over here you have the pole. You will have all the parallels of latitude appearing equidistant, that is proportional to the actual distance between them, and they are all concentric, right, till you say reach equator. At equator you might select the points from where to draw the meridians which are equidistant at equator, but when you approach the pole, you proceed in a manner so that whatever is the distance at any parallel is proportional to the actual distance on the earth, right? So you have drawn this meridian in such a way that distances on each parallel of latitude between the adjacent meridian is true, right? Likewise, you can draw the other meridians also, but the meridians don't reach the pole. So this is Bohn's modified conical projection. Distances are correct along the tangent meridian and also along each of the parallels of latitude. Next interesting projection is Polyconic projection. There are different types of polyconic projections. One of the popular ones is American Polyconic projection. So in this projection, you have a central meridian. You will draw various parallels of latitude. So suppose this is the parallel of latitude whose center is here. The next parallel of latitude would have center up there, and so on. They don't have the same, they are not concentric. They are circular, but they are not concentric. And likewise, you will go up to the equator, and then the trend starts this way. Now, how would the globe look in this projection? Would be something like this. Say you might find Australia here, you might find US, South America, so the globe appearing in the projection would be like this. These are the meridians, and the parallels of latitude. So that is American Polyconic projection.